All right, let's dive in. Today we are getting to the bottom of a really cool programming concept. How in the world your code keeps track of where it's been and where it's supposed to go next, especially when things get weird and it starts calling itself.
So this whole thing kicks off with a fantastic question, the kind you see on Reddit that really makes you think. It's simple, right? A function can call another function, no problem. But what happens when a function calls itself? How does it avoid getting totally lost in this digital hall of mirrors? How does it ever find its way back home? Well, the answer isn't really in the code you write, but in how the computer itself organizes its memory.
To really solve this puzzle, we're going to need a map. We first have to understand the landscape where our programs actually live, your computer's memory. And honestly, it's not nearly as complicated as you might think.
Okay, let's start way out in the suburbs of our memory map. Here, you've got your long-term storage, a hard drive or an SSD. This is where all your programs and data hang out when they're not being used. It's slow, sure, but it's permanent.
But when you actually double-click an icon and run a program, it gets loaded into a much faster, more exciting neighborhood called RAM. This is where the action is. This is the active workspace where all the real-time thinking happens. But look, we can throw all that hardware complexity out the window for now. Forget the circuits, forget the chips. For what we're talking about today, I just want you to picture memory as a giant, simple grid of boxes. That's it. And every single box in this grid has its own unique number, a label. We call it an address. And that's really the core idea. At its heart, memory is just one massive numbered list where we can stash little bits of information. So we've got this giant grid of boxes. How does a program actually use it to stay organized and not just make a huge mess? Well, it uses a very special structure called the call stack. And this right here, is the key to our entire mystery. I want you to think of the call stack as your program's personal to-do list. It's just a specific area of memory set aside for one purpose. Every time a function gets called, a new task gets added to the top of the list. And when that function is all done, its task gets crossed off. Simple as that. Now, each of those items on our to-do list has a proper name. It's called a stack frame, or sometimes you'll hear the term activation record. This is the basic building block. Every single time a function is called, boom, a brand new one of these is created. So what's actually packed inside one of these stack frames? Well, it's got three absolutely crucial bits of information. First up, the return address. This is the golden ticket, the breadcrumb trail. It tells the computer exactly where in the code to jump back to when this function is finished. Then you've got the parameters, the arguments that were passed into the function. And finally, it has its own private little workspace for any local variables the function needs to create. All right, deep breath. We have our map of memory, and we have our special to-do list, the call stack. Now, let's put it all together and watch how this beautiful system handles the mind-bending case of recursion. We're going to use a classic example you've probably seen 100 times, a function that calculates the factorial of 3. So, this function is going to call itself to get the factorial of 2, which will then call itself again to get the factorial of 1. Let's watch exactly how the stack handles this. Here we go. Our program starts by calling factorial 3. Instantly, a new stack frame is created just for this call, and it's pushed onto the top of the call stack. Inside this frame, we've got the argument 3 and, crucially, the return address pointing back to our main program. But wait, factorial of 3 can't finish its job yet. To get its answer, it first needs to call factorial of 2. So the program pauses what it's doing with fact of 3 and pushes a brand new frame for fact of 2 right on top. You can see the stack is already getting taller. And of course, you know what's next. Factorial of 2 calls factorial of 1. So a third frame gets pushed onto the stack. Now, this is the turning point. Factorial of 1 is our base case. It doesn't need to call itself again. It can just figure out its answer. The stack is now at its deepest point. Okay, so now the fun part begins. The stack starts to unwind. Factorial 1 returns the value 1. Its job is done. So its stack frame is popped or just completely removed from the stack. And here's the magic moment. Where does the program go now? It just peeks at the new top of the stack, finds that return address we stored in the fact2 frame, and jumps right back to where it left off. And now it's like dominoes falling in reverse. Fact2 has the answer it needed from fact1, so it can finish its own math and return its result. Its frame gets popped. Control goes back to fact3.
It finishes, its frame is popped, and we are right back where we started, with a totally empty stack and our final answer. Each and every function call knew exactly how to get back home.
Now, that whole process is incredibly elegant, but it has a very real physical limit. The call stack, just like any other part of memory, is not infinite. So what happens when we push it just a little too far? And this Reddit user, JXD13240, just nailed it when they said that if that chain of function calls goes on for too long, if it goes too deep without ever hitting a base case and starting to unwind, you just plain run out of room. You can't push any more frames onto the stack. And this catastrophic failure has a name you have probably heard a million times: a stack overflow. It's a critical error where your program tries to use more stack space than the system ever gave it. And the result, almost always, is your program just crashing hard. So it sounds like recursion is this double-edged sword, right? It's powerful, but it's potentially really dangerous. But what if? What if there was a way to get the elegance of recursion without the risk of that stack overflow? Well, there is. And it's a very clever little trick. Okay, check this out. On the left, you've got your standard run-of-the-mill recursive function. See how after the POW function returns, we still have to do that multiplication? The recursive call isn't the very last thing that happens. But now, look at the one on the right. This is called tail-recursion. Notice how the call to POW_accum is the absolute final action. There's nothing to do afterwards. It just passes its progress along in that extra accumulum parameter. And here's why that tiny change is a total game changer. When a smart compiler sees a function like the one on the right, it realizes, hey, there's no more work to do in this current stack frame after the next call, so why do I even need to keep it around? Instead of pushing a new frame and making the stack grow, it just reuses the current one. The standard recursion on the left makes the stack grow deeper and deeper, but the tail-optimized version on the right, it uses a constant amount of stack space. It's basically turned the recursion into a super efficient loop behind the scenes. No growth. You see, understanding how the call stack works isn't just some boring academic theory. It's the key to writing code that's not just clever, but also safe and efficient. It lets you debug really complex problems and design more elegant solutions. It really makes you wonder, doesn't it? What other invisible structures are quietly shaping the way we all program every single day?